for this webinar. So today we have the great pleasure to welcome Professor Yang from the Department of Physics at Fudan University in Shanghai. Professor Yang is a world expert on thermotics and thermal metamaterials. He has contributed really a lot to this field, which he actually also initiated. So, Professor, it's your turn.
Thank you. Okay, now can you hear me? Okay. First, I would like to thank the organizer. It's a big event to organize such a wonderful seminar around the world. So, many thank you to Bogdan and Milmer and Sebastian. Thank you. Okay, now let's start my. Let's start. Sorry. Okay, let's start my talk. Hello, I'm Jiping from Fudan University. It is really a difficult task to organize such seminars, but which is very important to the field. The title of my talk is Theoretical Symmetrics and Thermal Metamaterials, a brief review. In this talk, I'm going to present a brief review of thermal metamaterials and the accompanying series. My talk has 3 sections. That is introduction, research progress. Okay, let me use this one. And the summary and outlook. Okay, the first section is introduction. Traditional thermodynamics is an important discipline. It investigates natural systems and mainly focuses on passive description of macroscopic heat phenomena. Here, passive description means people can only know how to know such heat phenomena, but cannot change them at will. Certainly, as we know, the key theoretical framework of thermodynamics is the 4 laws of thermodynamics. Today, please allow me to introduce a different research direction, which is theoretical symmetrics. This is a new name I proposed in my recent monograph, published by Springer. To me, theoretical symmetrics investigates artificial systems and mainly focuses on active control of macroscopic heat phenomena. Here, active control means people can change them arbitrarily or at will. Clearly, this differs from the traditional thermodynamics. In contrast to thermodynamics, theoretical symmetrics has 2 features. First, theoretical symmetrics has a different theoretical framework. That is, it establishes and develops transformation, symmetrics, and other analytic extended theories, and then designs artificial systems or structures in order to control heat transfer with novel behaviors or properties. Second, theoretical symmetrics has a direct application value. That is, it helps to design and fabricate materials for controlling heat, namely thermal metamaterials. Now, let me show you the search results from Google and Bing about thermal metamaterial and metamaterial. Clearly, the occupation ratio of thermal metamaterial to metamaterial is always between 16.7 to about 40%. This clearly indicates the popularity of thermal metamaterial in the field. Here, I should also mention that so far the connotation of thermal metamaterial has been extended from treating thermal conduction only to treating not only thermal conduction, but also thermal convection and thermal radiation. Now, Let us glance at the history of metamaterials for sketch profile. Please see this paragraph. Metamaterials originate from wave systems. It is shown that refractive index of electromagnetic waves is usually positive, which means positive permittivity and permeability. While in the 1968, Vesnago challenged this common sense and proposed the assumption of simultaneous negative permittivity and permeability, which yielded a series of anomalies in electromagnetic wave transfer phenomena. However, the Russian physics idea did not receive attention until the 1990s. In the 1990s, Penty and collaborators successfully experimentally obtained effective negative permittivity and permeability in the microwave band with metric rods, periodic arrays, and split ring resonators. Since then, the field of metamaterial physics has grown vigorously. In 2006, Penty etc. developed a mathematical tool for design metamaterials, which is called transformation optics, and they proposed the famous concept of invisibility cloak. The cloak just relies on negative permittivity and permeability. Another significant work in wave system came from Professor Shen's group from Hong Kong. Shen led the invention of locally resonant sonic materials that initiated the field of acoustic metamaterials. Their work inspired the subsequent metamaterial researches beyond electromagnetic wave systems, including those in acoustics, elasticity, and mechanics. On the other hand, the concept of transformation optics was extended from wave systems to diffusion systems in 2008. This aroused the subsequent enormous research of thermal metamaterials. This page comes from our APR paper published in 2008. It developed the theory of transformation semantics for steady-state thermal conduction, and it proposed some new concepts, including thermal clocking and apparently negative thermal conductivity, namely thermal rotator. Here, cloak means the heat can flow around an object as if it does not exist. What is the theory of transformation semantics or transformation thermodynamics? Here, kappa is the thermal conductivity of a homogeneous medium, and kappa tilde is the thermal conductivity of an inhomogeneous medium. For the homogeneous medium, heat can flow along a straight line if we do not care about dissipation. Then, if we twist and squeeze or stretch the homogeneous medium, this medium naturally becomes inhomogeneous. For the inhomogeneous medium, clearly, heat will flow along a non-straight line. In other words, we can use inhomogeneous medium to control the flow of heat along specific directions. In this way, the thermal conductivity kappa tilde of the inhomogeneous medium can be determined according to the formula, like this one. From this formula, we can find that the kappa tilde is determined by kappa and J. Here, J is the Jacobian matrix, which describes the space transformation from the homogeneous medium to the inhomogeneous medium. This formula is a result of transformation semantics or thermodynamics. In 2008, we gave the steady-state version, and in 2012, Professor Sebastian Gallulli derived the non-steady-state version with much more details. After 2008, our APR paper did not receive any attention from the scientific community until 2012. Fortunately, in 2012, a group from Harvard University published a paper in PIR. In their paper, they experimentally demonstrated the behavior of thermal clocking. They used an AB-AB structure. After that, many other papers have appeared in PIR. And they have also experimentally demonstrated thermal clocking by using different structures and different conditions. So there comes a research upsurge of achieving novel thermal transport via designing artificial structure by developing transformation semantics. Many articles have cited our paper as the first reference in the field of transformation cymatics. Okay. Since 2012, I was also reported by Science, and our work was introduced in a review work published in Nature. Further, both Nature and Science introduced the field into other short papers. One title is Cloaking of Heat, and the other is Metamaterials Beyond Optics. Also, Nature Materials also published another short paper and indicates the pioneering contribution of the APR published in 2008. After that, we returned to this field again, and we published new papers in PIR. And also some papers have received some good attention from the scientific committee. This review paper was published in Nature, and it was written by Mardovan from MIT. It adopted for the first time material to name thermocrystal and relevant devices designed by using transformation cymatics, thus yielding the direction of thermal metamaterials. Our APR paper was cited and also received some positive evaluation. Now, some people may ask, what is thermal metamaterial? Thermal metamaterial means those materials or devices with artificial structures that can be used to control heat conduction, convection, and radiation in novel manners. In this case, geometrical structures rather than physical properties play a dominating role. This fact makes thermal metamaterials different from other materials, including thermoelectrical materials and so on. For the latter, physical properties rather than geometrical properties structures play a dominating role instead. So far, thermal metamaterials have obtained commercial applications. For example, this slide shows some commercial products which are designed and fabricated according to radiative cooling. Such products can be bought from the market. For more details about the physical mechanism, please refer to this science paper published in 3 years ago. Due to the good progress of the field, I have published a monograph on transformation cymatics and thermal metamaterials. The book was just published this January. This year, I also attempted to organize an international conference on thermodynamics and thermal metamaterials. This is the group photo for ThermoMet 2020. On the other hand, I also held the national conference last year. The second part is research progress. Here, I would like to take this opportunity to summarize the research progress of thermal metamaterials according to the 6 kinds of theories. Such theories can help to design thermal metamaterials. So the progress contains 6 parts. In the first part, I would like to introduce the results obtained from transformation cymatics. The thermal cloak is the first fantastic phenomenon of transformation cymatics, which was theoretically predicted in 2008. So, what is thermal cloak? It has 2 remarkable features, namely protecting the central region from external heat flow and not disturbing external thermal field. Generally, this phenomenon only exists in fictions, but by using the power tool transformation cymatics, humans first have the chance to achieve it. Through the spatial compression operation from the central point to the inner layer, the requested thermal conductivity tensor of shears can be obtained with the help of Jacobian matrix. The first experimental demonstration in 2008, in 2012, adopted Martinez structures to achieve the requested thermal conductivity. It has stirred up thermal metamaterial research booms till now. In 2015, our group developed transformation cymatics to describe temperature dependence of thermal conductivity. As a result, an intelligent thermal cloak is designed. It can switch cloaking functionality under different temperature regions. The thermal cloak has potential applications in deceiving detection, thermal protection, intelligent temperature control, and temperature preservation. Thermal concentrator is another representative phenomenon obtained from transformation cymatics. Contrary to thermal cloak, thermal concentrator can focus heat flow in a central region, like this one and this one. Similarly, the external temperature fields are also not disturbed. Okay, we can see here. Through the spatial stretching and the compression operation in transformed layers, the radial components of transformed thermal conductivity tensors are larger than the tangential components. So the concentrating effects can be achieved based on temperature-dependent transformation symmetrics. An intelligent thermal concentrator can also be designed like this one. Thermal concentrator has applications in energy connection, especially it may improve thermal electric conversion efficiency from a different perspective. Based on thermal clocking and concentrating, dual function was proposed accordingly. Here, dual function means two different functions, such as clock and concentrator, are achieved simultaneously on a single device. It can also be classified into categories, marked fields and monofields. The former denotes two different functions are realized in marked fields, such as thermal clock plus electric clock, thermal concentrator plus electric clock, thermal concentrator plus electric concentrator. The latter refers to, for example, thermal clock plus thermal concentrator. These two categories of dual function have different theoretical foundations. The marked field dual function is based on the similar forms of governing equations. However, the monofield dual function relies on temperature-dependent thermal conductivities. As a usual application, the dual function may benefit to device integration and marked field control. Thermal rotator can help to rotate heat flow in the transformed region. This is due to the angular transformation in the transformed region, and thus the asymmetrical thermal conductivity tensors. Thermal rotator can be used for detection. So far, I have introduced the three representative thermal metamaterials, namely thermal clock, concentrator, rotator. DD, etc. Combine these three structures on a single printed circuit board to realize the efficient heat dissipation of electronic devices. They arrayed the optimized copper fiber configuration on printed circuit board for realized anisotropic thermal conductivities, which were required by the clock, concentrator, and rotator, like this one. The experimental results indicated that, compare this value and this value, the results indicated that the temperature can be lower than the condition without the design structure or with the other structure. This shows a good performance in thermal dissipation. Macroscopic thermal diode is a direct application of temperature-dependent transformation symmetrics. It is based on the switchable thermal clock. The transformed layers are constructed with shape memory alloys. When different temperatures are applied on the transformed layers, the thermal conductivities will change due to deformation. Here, we use two different types of shape memory alloys. They have similar phase change temperatures, but inverse phase change directions. As a result, the device is insulating from left to right, but conducting from right to left. This kind of device may have potential applications in temperature preservation, heat dissipation, and logic gates. Thermal illusion means that a non-existing object exists in infrared imaging, replacing the original existing objects. Some researchers experimentally fabricated an illusion device which can make one heat source look like four heat sources, like this one. The fundamental mechanism still lies in transformation semantics. Our group also developed a method to distort the temperature distribution signature of an object, this one. As a result, the target object accurately exhibits the same temperature distribution signatures as another object that is predetermined, but actually does not exist in the system. These devices have potential applications in infrared detection. The second part is the heat conduction equation. By directly solving heat conduction equation, a binary structure was theoretically proposed and experimentally verified for clocking heat flux with isotropic materials. This does not rely on extreme parameters required by transformation symmetrics. This method overcame the weakness of transformation theory and offered a convenient scheme for thermoclocking. Recently, Li etc. extended the zero-index concept from photonics to thermoclocking, to thermomaterials, and designed a zero-index thermoclock. The analog of a zero-index is an infinite thermoconductivity. They defined the inner layer metamaterial as infinite and deduced the analytic solution to the conduction equation. In this case, the outer layer has a smaller conductivity than the background. The infinite parameters of the inner layer were effectively achieved by convective elements. The first row shows the temperature distribution of binary thermoclock. The second row shows the temperature distribution of two objects outside the thermoclock. The third row shows the temperature distribution of the two objects only. Compared to the second row and the third row, we know people cannot detect objects inside the core. They cannot detect only by measuring the temperature distribution outside the shear. So this is called camouflage, which is useful in some particular areas. Okay, now let's move to the other phenomenon. Although transformation symmetrics has advantages to control heat transfer, it also leads to severe problems such as anisotropic, inhomogeneous, and even singular parameters. They limit practical applications. To solve this problem, thermal transparency is proposed with the concept of neutral inclusion. The method only requires isotropic and homogeneous parameters, which largely reduces the fabrication difficulty. The simulation results are shown in the first row, this one. The left picture is a core embedded in the background. Due to the thermal conductivity mismatch, the thermal field is distorted. Then the core is coated by a designed shear. See this one. And the distortion of thermal field can be neglected. Therefore, thermal transparency is achieved. The second row shows an experiment set up for validating the simulation results. Thermal transparency has potential applications in reducing thermal stress concentration. The above thermal transparency is based on co-shear structures. Our group has also extended this behavior from co-shear structure to many particle systems. How to design a specific thermal image is crucially important in some areas. Although the attempts of cloak or transparency are exciting, there is still a distance from practical applications. Here, we propose a simple but more feasible scheme to design arbitrary thermal images. The left figure is an infrared image of a real person. We extract the information in the yellow frame. By discretizing the chosen temperatures, we can get a series of pixels. We design mixtures with different thermal conductivities for these discrete temperatures. In this way, we can obtain the designed thermal conductivities like this one. This picture is a schematic diagram of our sample, this one, whose thermal conductivity distribution is shown in this picture. Different colors denote different thermal conductivities. We then put the sample into a constant heat reservoir. So the back surface of the sample has a constant temperature. Since the sample has a certain thermal conductivity distribution, the measuring temperature distribution on the front surface are as expected. See this picture. Clearly, it looks like the infrared image of a real person. Gold touch is a long-standing dream of human beings. For this purpose, we make an attempt to approximately realize this phenomenon in thermotics. In general, a normal case is represented by the black line. The effective parameter of core shear structure slowly increases with the core fraction, which is consistent with our common sense determined by effective medium theory. Here, we define gold touch as shown by the red line. The effective parameter increases sharply when the core fraction is very, very small, or exactly speaking, close to zero. In other words, the core property can be extended to the shear region with an extremely small core fraction. This phenomenon is based on a core shear structure where the core is a scalar parameter and the shear is a tensorial parameter. By calculating the effective thermoconductivity of such a core shear structure, we can obtain some specific conditions to meet the requirements of golden touch. The results are shown in the right figure. Clearly, with the increment of the core fraction, the core property quickly extends to the shear region. This phenomenon can be used to design thermal conductivity at will. For the core shear structure, if we set the shear to have a scalar thermal conductivity and the core to have a tensorial thermal conductivity, we can arbitrarily rotate the heat flux in the core with different angles, like this one with different angles. Meanwhile, the heat flux outside the core shear structure still keeps unchanged, as if there is nothing, there do not have other objects in the central region. Here, nonlinear thermal conductivity means temperature-dependent thermal conductivity. Accordingly, linear thermal conductivity means the thermal conductivity which does not depend on temperature. By applying the effect medium theory, we can approximately calculate the effective nonlinear thermal conductivity of core shear structures. See the upper figure. We then use the Taylor expansion to calculate the nonlinear enhancement under resonant conditions. The results show that the nonlinearity can be effectively modulated and enhanced. Here, enhanced means eta is larger than 1. The results are shown in this figure. The value 1 is plotted with a dashed line. The data above the dashed line indicates nonlinearity enhancement, and that below the dashed line means nonlinearity reduction. This scheme has potential applications in intelligent control. Such extreme thermal conductivities are always a hot topic. This work reported a material with extremely low thermal conductivity. The material belongs to error gears. The results show that such a material has an extremely small thermal conductivity, 0.024 in the vacuum and 0.02 in the air, which is even smaller than the thermal conductivity of the air. This is the thermal conductivity for the air, 0.026. In their design, they have resorted to the two novel effects. One is negative Poisson ratio, and the other is negative thermal expansion coefficient. Such a material has potential applications in heat protection. The third part is phase transition theory. Maintaining a relatively stable temperature is important for electronic chips and buildings. However, energy is always needed to keep warm or cool. Here, we demonstrated that it is possible to keep a region between hot and cold ends at a constant temperature without the need of consuming external energy. For this purpose, we have designed a zero-energy thermostat. These simulation results are shown in the left figure. Clearly, as the temperature at the right boundary increases significantly, the central temperature keeps almost unchanged. Therefore, this structure can work as a thermostat. To validate the theoretical predictions and the finite element simulations, we also performed experimental results, which is shown in this slide. The experimental results agree well with the simulations, confirming the feasibility of the thermostat. Such a design is based on phase-changing materials and has potential applications in energy saving. We have discussed how to design an energy-free thermostat in the previous slide. A further question is whether the thermostat can generate energy. In this way, the thermostat can not only maintain a constant temperature in the central region, like this one, but also generate electric energy. That's called negative energy thermostat. To this question, our answer is yes, as long as we additionally take thermoelectric effects into consideration. We apply environmental temperature gradients, which can simultaneously generate electric currents because of the thermoelectric effect. The left column shows the simulation results. Here, A and B are two different thermoelectric materials. Although the temperature of the right boundary changes significantly, the central temperature keeps almost unchanged. Therefore, this structure can work as a thermostat. Meanwhile, from the right column, we can find that an electric field is generated indeed. Therefore, we can not only maintain the constant temperature in the central region, but also generate additionally electric energy. Such a device has potential applications in the area of energy saving. The first part is energy band and quantum theory. Periodic structure has been widely explored in atomic crystals, photonic crystals, and phononic crystals. As inspired by these pioneering results, Monograph also proposed the concept of thermal crystals to control heat transfer at micro and nanoscales. As you know, the Fourier law is no longer valid in the nanoscale, where phonons are the carrier of heat conduction. So the method for manipulating heat transfer at such scales is very, very different from that at the macroscopic scale. To solve this problem, Monograph considered an alloy with periodic air cylinders. In this way, thermal band gaps also appears for this structure, which is similar to those in photonic crystals or atomic crystals. As a result, heat transfer can be effectively controlled by tailoring the band gap structure. Thermal crystals have broad potential applications, such as design, heat waveguides, thermoanalysis, heat imaging. Here, this is a heat source, and this is a heat image. This means heat flow along this way, and then it at this point. Here we find negative reflection appears due to the periodic structure of thermal crystal. And also, thermal crystal can be used to design thermodiode. Here, thermodiode also means heat can flow from left to right, but cannot flow from right to left due to the periodic structure. Also, thermal crystal can also be used to design thermal clocking. Certainly, the mechanism is quite different from previous mechanisms, such as transformation symmetrics or by solving thermal conduction equation directly. Generally speaking, there are three basic modes of heat transfer, including thermal conduction, thermal convection, and thermal radiation. The first two modes are dependent on metals, so they do not exist in vacuum, which is a common belief. Certainly, because the third mode, namely thermal radiation, is essentially the propagation of electromagnetic waves, it can exist in vacuum. However, this work changes our belief and shows that superconduction can also exist in vacuum. The underlying mechanism lies in quantum fluctuation. In fact, the vacuum is not absolutely empty. The uncertainty principle tells us that there is quantum fluctuation in vacuum. In this way, heat energy can be transferred through quantum fluctuation. Although this work is not the theoretical prediction of heat conduction in vacuum, it is the first experimental validation. Therefore, heat conduction is experimentally proved to exist in vacuum. But here I have to say, for this result, heat conduction in vacuum, the first experimental predictions can be found in such papers by theoretical analysis. I think such theoretical analysis is very good. For this paper, recently, some other scholars have some different thoughts about the experimental procedures. So if you have interest, you may read this article. Okay, anyway, this work has applications in nanoscale heat conduction, such as enhancing thermal transport efficiency at the nanoscale. The fifth part is thermal convection. Thermal convection is a widespread phenomenon in nature, so its effective manipulation is particularly important for industrial application and daily life. For this purpose, our group studied the conduction and convection equation and established the corresponding transformation theory to control conduction and convection simultaneously. The first row shows the results of thermal convection cloak. The left one is the temperature distribution. The middle one is the speed distribution. And the right one is the heat flux distribution. Compared with the simulations in the last arrow for the same distributions for only background, the temperature distribution, speed distribution, and heat flux distribution in the background, this distribution is the same as this one, and this distribution is the same as this one. Therefore, the convective cloak can also be used to avoid the central object from being detected, which has potential applications in thermal dissipation detection. The middle row shows thermal convective concentrator. The background distributions are still not distributed if you compare this background and this one. Meanwhile, the temperature distribution, speed distribution, and heat flux distribution are all concentrated compared with those in the background. Our analysis is based on the transformation theory. For this area, for thermal conduction convection, for this area, this is the first proposed by Professor Canulio in 2015. Such a design has potential applications in collecting convective energy. Similar to camouflage in thermal conduction, camouflage in thermal convection can also be designed on the same footing, such as these two different objects outside the convective cloak. And for this picture, we find if we put the same four objects in the same position, but keep in the pure background, and then we found the distribution of temperature or speed or heat flux are the same as those in the region where only background exists. Anti-parity-time symmetry is a crucially important concept in various systems, which, however, are always wave systems. This work is the first to reveal anti-parity-time symmetry in a diffusion system by considering two moving rings with equal but opposite velocities, which are connected together by a stationary intermediate layer. The authors find two different states of temperature profiles, which are determined by an expressional point. When the rotation speed is smaller than the exceptional point, the system is in an anti-parity-time symmetry region. Therefore, the temperature profile in the two rings are both motionless with a certain phase difference smaller than pi/2. When the rotation speed is equal to the exceptional point, the temperature profiles in the two rings are still motionless with a phase difference of pi/2. When the rotation speed is bigger than the exceptional point, anti-parity-time symmetry is broken. Therefore, the temperature profiles in the two rings are both moving, like this one. These results have potential applications in controlling heat and mass transfer. The sixth part is thermal radiation. Beyond conduction and convection, radiation is also a basic mode of heat transfer, which exists everywhere in nature. Therefore, how to effectively manipulate radiation becomes particularly important. For this purpose, we study thermal radiation with the Rossland diffusion approximation. This treats the propagation of photons as diffusion. In other words, the mean free path of photons is much smaller than the system size. So photons of thermal radiation propagate only a short distance before being absorbed or scattered. This occurs in many practical materials like aerogels. For such a problem, we developed the effective medium theory to control thermal radiation. By performing a variable substitution, we can transform the nonlinear Laplace equation into a linear one. Here, nonlinear means that thermal conductivities are temperature dependent or thermally responsive. And linear means that thermal conductivities are temperature independent. We then design three practical devices, including transparency and the cloak and the expander, as potential applications of the theory. See the first, second, and third columns, respectively. These devices can help to control thermal radiation with a different manner. But I believe much more work should be done or could be done in this field about thermal radiation. There are many new physics we should try to review. Another key application related to thermal radiation is daytime radiative cooling. It sounds impossible, but actually possible. Simply speaking, two steps are applied to realize this purpose. Firstly, one needs to reflect the thermal radiation from the environment to avoid absorbing heat energy. Secondly, one should enhance the radiation from the object to the environment in order to release heat energy. In this way, daytime radiative cooling can be achieved. Concretely speaking, a photonic crystal structure can be applied to increase the emissivity in the atmosphere window. See this picture. Their experimental results agree well with the theoretical predictions. See this picture. Such a device can reduce the temperature about 5 K. It is a good result because if the temperature can be reduced about 5 K, it is very cool in summer. Okay, such a phenomenon and the mechanism has been put into the commercial use and produced tremendous benefits. as I have mentioned in the introduction of my talk. Now, let's move to the final section, summary and outlook. Theoretical symmetrics is a new name I proposed in the recent monograph published by Springer. To me, theoretical symmetrics investigated artificial systems and mainly focuses on active control of macroscopic heat phenomena according to transformation, symmetrics, and other analytic extended theories. As a result, several metamaterials come to appear. This starts from 2008, when my group and Chen's group extended the concept of transformation optics from wave system to diffusion system successively. This has aroused the subsequent enormous research of similar metamaterials, especially after 2012. In summary, in this talk, I have presented some research progress of similar metamaterials. Here, I have to emphasize such progress. When I introduce such progress, I have combined with the research results obtained by my group. Anyway, I believe much more research should be conducted, such as those related to thermal conduction, thermal conduction convection, thermal conduction radiation, and thermal conduction convection radiation. To me, for such different systems, many new physics can be revealed, such as multi-stability. And we also designed a thermal conduction convection crystal. For this crystal, we also can use this to control the flow of heat. Also, we also developed a theory to describe heat conduction convection by using complex conductivity. Use this concept, we can describe the phenomena well. Also, we also develop a new transformation method for considering such system. And for practical applications, I think we have to try to include as many heat transfer modes as possible, such as heat conduction, convection, radiation. Actually, for such system, we can theoretically design and fabricate, restructure meta surface. For such meta surface, we can obtain desired infrared imaging of different or of arbitrary objects. Okay, that's all for my talk. Thank you for listening.
Thank you very much, Professor Huang, for this very nice talk, which spans many topics in physics. So I guess there would be lots of questions from people who attended this talk. So please, people come forward with your questions.
So